Hi class, we are now on chapter 18.3. We're going to look at a buffer's effectiveness, buffer range, and buffer capacity. So a buffer is only good as long as it can neutralize amounts of acid, added acid or added base, and still stay as a buffer, meaning that the amount of acid or base added does not overload the system where it's no longer a buffer system. And there is a limit to how much can be added before the pH changes significantly, because once it does, that means it's no longer a buffer system. So this the buffer capacity is the amount of acid or base a buffer can neutralize. Anything past that, it's no longer a buffer system. The buffer range is the pH range in which the buffer can be effective. Remember I mentioned in the previous section that we have buffers in all pH ranges. So you want to have one that's specifically in the pH range that you want, and you want to know what that range is so it can be effective. The effectiveness of a buffer depends on two factors. So we want the amounts of buffer and acid, the amounts of buffer acid and base. So the amounts of both of these, and then the concentrations of both. So the first one's looking at a ratio of how much acid there is to base, and the second one is straight what it says, concentration. So the effectiveness of a buffer will be most effective when we're looking at a ratio of acid to base. So what does this mean? Think of equal concentrations. So if you have equal concentrations of the acid and base, let's say one molar to 1 molar, so if the acid's 1 molar and this is 1 molar, so 1.0, 1.0, and if you divide these, it's a ratio of 1. But if you have anything that's not equal in the same value, then you're not going to have that 1. So to be an effective buffer, you want to have the molarities, the concentrations, to be as close to each other as possible, so you can have this equal to 1. If you divide one by the other, it comes out as 1. And the only way to do that is have the concentrations being the same value. A buffer can also be effective when it's only within a certain amount of range. So that range is between 0.1 and 10. So remember when I said by dividing these, because we want a ratio of them. You don't want anything below this and anything past this, because if you get anything past you don't want it to be past 10, because then it's not going to be effective. So when you create a buffer, you want to make sure that these things that can make it as most effective as possible, that we meet that criteria. So one is to have a ratio that is equal to 1 or close to it, or have a ratio that's within this range of 0.1 to 10 and nothing outside these limits. Also, a buffer will be most effective when the acid concentration and the base concentration are large. So we're going to look at that here. So if we look at different concentrations, so let me go through this first one. This is an example in your book. We have an acid, and we start out with a mole of 0.1. Now we have an addition of a base that's been added to it. So when it does, we subtract the amount that was used up, and we end up with 0.90 mole. Now that base, using we have to add that base over to this is the acid and the conjugate base. So we add this over, and it produces a result of 0.110 mole. Now we're going to use this in this equation that hopefully you guys are very familiar with by now. It gives us the initial pH as 5.0. And it also gives us the pK at 5.0 that I didn't write down. So I forgot. So we plug this in, the bases over the acid, and it gives us our new pH with these different amounts with the addition of a base as 5.09. The initial pH was 5.0. So we want to know the percent change, the pH percent change in this. And it changed by 1.8%. How did we know that? Well, you take the difference, the new pH, subtract it by the old initial pH, and divide it by the initial pH, times it by 100. This gave a percent difference with the addition of that 0.10 mole of base as 1.8%. Now, let's look at one situation where the concentrations are not equal, or the moles are not equal. So in this case, we have an acid, an initial amount is 0.18, but we add the same amount of base, which produces now 0.17 mole. Now we look at the base, the conjugate base, and we start out with, oh, sorry, that's weird looking. Pretend this part isn't here. Is 0.020 mole. This is straight from your book, so there's an example of this. And we add that additional base, and that produces 0.30 mole. So now we have two different amounts. These are different amounts, but these are larger differences than these differences. And these started out with the same initial concentrations. So as we go through here, we can look at this and set it up in the same way. pKa is 5.0, which I forgot to put on here. Set up the same log, and the pH now is 4.25. So here the initial pH was 4.05. So we're going to plug this in to see the difference in percent change. So we have 4.25 minus 4.05 over 4.05. Both these are the initial pH. And we see that the percent difference is a lot larger. It's almost 5%. So having concentration, or moles in this case, that are different from each other, and this is, if you look at it, this started out with 0.18. This is supposed to say 0.020. There's still a big difference between those. There's a big difference, and you can see that just those difference of the moles of the acid and the conjugate base creates a difference in 5% compared to something that's almost 2%. So if we want an effective buffer, we want to keep the concentrations, or the moles, very similar to each other. Yes, there will be a difference because of the addition, but if we keep these similar to start out with, then the difference between them isn't as large. So buffer range. We said that the buffer range, we want to have a ratio of these to be between 0.1 to 10, and that's the most effective range. Anything outside of that. So substituting into the Henderson-Hasselbalch equation, we can calculate the maximum and minimum pH at which this buffer will be effective. So if we need to create a buffer, we need to also know what pH, what range of that pH it can handle. That's very important because the pH will change by adding the addition of base or acid. So it's good to know that. So in this case, we are actually looking at the pKa. So to have the lowest pH, what we do is we take the pKa minus 1, and that will tell us the range of the pH. Here we take the pKa plus 1 for the highest pH, and that will tell us what is the range of this. So whatever the buffer is, whatever the acid, the weak acid and conjugate base we're dealing with in this case, we can find the pKa and minus 1 from that. We can find that pKa again and plus 1, and that is going to tell us what the pH range in this is. So the most effective pH range of a buffer is you take the pKa of that, and all of these have pKa values to them, and you take the plus and minus of 1, and that's going to tell you what the pH range is. Okay, so buffer capacity is the amount of acid or base that can be added to a buffer without causing a big change in the pH, because remember, every time we have an addition of an acid or a base, it does change the pH. It may be small, but eventually, if you keep adding, it will eventually change it to the point that it's overloaded, even with small amounts, because when we create a buffer, we use very large amounts of the weak acid and conjugate base, but they do get used up. So in this case, there is the capacity. Eventually, it's going to hit the capacity where it can no longer change by a small amount, and it will change by a large amount in the pH. So the buffer capacity increases with increasing concentration. So the concentration helps because the higher the concentration, the more it can neutralize. So you want to have something that will will have a buffer that will be really resistant to pH changes as much as possible. So one of the things is you want to have a large concentration of both the weak acid and the conjugate base. Also, having a large concentration of them help, because the higher the concentration, the more they can be neutralized. Also, again, approaching the ratio as 1, there is a range, but ideally you want it as close to 1 as possible. But that will help improve to neutralize either the acid or the base. Now, buffers that need to work mainly with added acid generally have a higher concentration of base to acid, and that would make sense, because if the acid is being added in, it's the base that's going to have to react with it, and that's why it would be beneficial to have more of a concentration. You can still keep it in the ratio range, but you still want to have more of a concentration of base to acid. And the other way is buffers that need to work mainly with added base generally have a higher concentration of acid over base, because of the fact that the acid is going to have to interact and neutralize that base. So you're going to have to, it's going to work harder on that side compared to with the base. So the effectiveness is based on two factors, buffer capacity and the effective pH range. So the buffer capacity is how most resistant to pH changes, and effective pH range. You want a specific range, and you want that buffer to stay in that range and not to be outside of what it is that you would be working with. So buffer capacity refers to the ability of a buffer solution to resist a change, which is what we want. We don't want the pH to change a lot. Buffer capacity is dependent on the concentration. So we want the concentrations, again, to be high concentrations, and we want them to be as equal to each other. That tends to show, based on what I showed as an example, that there is smaller change within that than something that has two different concentrations. And buffers are most effective at pH values within 1 pH unit of a pK value. And the pK values are easy to find. So that once you know the pK value, you do a plus and minus 1, and that will allow you to understand what the pH range is of that buffer and if it works with whatever you would be working with. So buffer capacity, a concentrated buffer can neutralize more acid or base than a dilute one. This is a perfect example. You see we have more here than we have here that will interact. So this would do a better job neutralizing additions of acid or base to it compared to this. So we want a stronger concentrated buffer. All right, a 1 liter buffer solution is 0.1 molar in HF and 0.050 molar in sodium fluoride. Which action destroys the buffer? So let's take a look at these. So let's just start here. See, if we're adding more of this, that's just adding more of this, and it would shoot the equilibrium. So this one's not going to do anything. We're looking at a base here. There's already a large base. So this one isn't one we're actually concerned with. This one here, the HCl, this is the one that would actually cause problems because this has to interact with this. And this one is a lower concentration than the weak acid. So this will get used up and there will still be weak acid left. However, this will use up the entire amount of the conjugate base. So once it uses up all of it, there is no more conjugate base to the weak acid, or there wouldn't be enough. So now it's no longer considered a buffer system. So it's the HCl that's going to cause the problems because it's going to use up the entire conjugate base compared to the others. Okay, so review. Buffer capacity is the ability of the buffer solution to resist a change in pH when an acid or base is added. Buffers resist a pH change most effectively when the concentrations of the weak acid and the base are equal, and high concentrations as well, because the higher they are, the more effective they are at neutralizing that acid or the base that's been added. We can also look at the pKa values, the plus and the minus one, and that will help us determine as well to get the best pH range for what we want to work with.